Okay, let's dive right into Chapter 17, Electrochemistry. That means we're going to be dealing with batteries and the chemicals that we use to make batteries. So, quick refresher on electricity. Remember that everything flows downhill. They want to minimize their electrical potential energy. Even if it's, they want to minimize any potential energy, even if it's electrical potential energy or chemical potential energy. Now, for batteries, what that means is that when chemicals exchange electrons, we let those batteries flow across a wire. So they're flowing downhill from one chemical to another. And as they flow downhill, sort of like water flowing down a river, we catch them and make them do work in the electrical equivalent of water wheels. So all electrons have a negative charge of 1.602 times 10 to the negative 19th coulombs. A coulomb is just the unit of electrical charge. Electrical potential is measured in the volt, which is 1 joule per coulomb. Okay. So if you raise an electric charge across 1 volt, you will have done 1 joule of work per coulomb of charge. So the volt is the measure of electrical potential energy. It's like the height of the hill that the charge is going up or down. In physics, you learn about circuits and what goes in them, things like resistors and capacitors and things like that. In chemistry, you learn about the battery, why the electrons are traveling around the circuit. Now, redox reactions are the heart of the battery. Redox stands for reduction and oxidation. In a redox reaction, electrons are fully transferred from one species to another. This stands in contrast with reactions like the combination of hydrogen and oxygen to make water. At the end of that reaction, hydrogen and oxygen are sharing electrons. They haven't fully transferred them. It can be kind of complicated, the way electrons are transferred, though, and it can be, not entirely obvious how many have been transferred. So there's some formalisms, things that you have to know about in order to deal with this. Some of you may have seen this before in your first semester, but we'll be going through this nevertheless. The first formalism is the oxidation number. That is not quite the same thing as electrical charge, but it's close. And there are ways to determine what an oxidation number is, and we'll be getting into that shortly. But it represents, how many electrons an atom, I should say, has gained or lost compared to its pure elemental state. Reduction is the change in oxidation number related to a decrease in oxidation number. Okay? That's why it's called a reduction, because the number is going down, because it's gaining electrons. So that can be confusing or annoying, because the reduction is the gain of a thing. Just remember that the reduction is happening to the number, and it's happening because it's gaining a negative charge. Oxidation is the opposite of reduction. It's an increase in oxidation number, the loss of electrons. And this is named for the fact that when things are oxidized, when they react with oxygen, they usually lose electrons to oxygen. Oxygen is reduced when that happens. Now, paired with oxidation and reduction, you get the oxidizing agent and the reducing agent. And this can also cause some confusion. The oxidizing agent is the thing that causes oxidation. So it causes another thing to be oxidized. So the oxidation agent itself is reduced. And that's why it can be kind of confusing. Similarly, you get the reducing agent. The reducing agent causes reduction in something else. So the reduction agent is oxidized. Hopefully this little diagram will, at the very least, help. These are the rules for finding oxidation numbers. The first is that the sum of the oxidation numbers for all of the atoms in a compound equal the charge of the compound. For example, here we have carbonate, CO3 2 minus. 1 carbon plus 3 oxygens equals a total of 2 minus. Here we have permanganate, MnO4 1 minus. 1 manganese plus 4 oxygens equals 1 minus. And then we have ammonium, 1 nitrogen plus 4 hydrogens equals 1 plus. I should probably have drawn a neutral species on here as well, say carbon dioxide or water. Those would add up to 0. If it's a neutral species, they add up to 0. It's an oversight on my part. But that is fairly simple, fairly straightforward, I hope. And our next rule is that the oxidation number of a pure element is always 0. Hopefully this won't throw too much of a monkey in the wrench. You should, by now, recognize the diatomic elements, oxygen, hydrogen, chlorine, and so on, Brinkelhoff. The metals, it's just a metal all by itself with no charge. Some of the other non-metals can be strange. For example, phosphorus has the strange allotrope P4. Sulfur has S8. If you're not sure, if you see an element all by itself with a weird number, go ahead and ask me. I will always tell you, unless I'm feeling very angry. I'll always tell you. But a pure element is always 0. Okay? So that should be straightforward enough. Next up, we have our monatomic ions. That means a single atom with an ionic charge. Nice and straightforward. So aluminum 3+, just a 3+ oxidation number, or +3. Iron 2 is 2+, iron 3 is 3+, chloride is 1 minus. It doesn't matter what the charge is, it's the element all by itself with a charge, that's the oxidation number. And now we start with the nonmetals in compounds, where things can get a little complicated. They're not very complicated, it just takes a little bit more effort. First up, we have hydrogen. Hydrogen is always +1 if it's bound to a metal. If it's bound to a nonmetal. Hydrogen is +1 with nonmetals. And if it's bound to a metal, it's -1. Okay? It's a hydride when it's bound to a metal. So here we have some examples. Whether it's in water, or hydrogen peroxide, or hydrogen chloride, or ammonia. Hydrogen is always +1. And down at the bottom, it is bound to some metals. You have sodium hydride, aluminum hydride, and lithium hydride, where it's always -1. So there you have a clue that can help you understand and remember. If it's called a hydride, it's -1. That's your verbal clue. If it's bound to a metal, it's -1. That's your other one. And now we have fluorine. Okay, fluorine is simple. Fluorine is the most electronegative element, so it always gets its way. Okay, it's the big tough guy, it's a jerk. It's always going to be -1 or 1 minus when it's in a compound. So hydrogen fluoride, this fluorine chloride or fluorine dioxide, it would always be -1 in those cases. What about over here on the right? F2, pure element. Elemental fluorine is 0. The only thing fluorine can't boss around is itself. There's a metaphor there somewhere, I think. Moving right along, we have oxygen, a little bit more complicated. Oxygen is the next most electronegative element. It's the number 2, and that might help because it's always 2 minus, unless it's a peroxide or bound to fluorine. So up top here, we have just regular old oxygen compounds. We have water and chlorate and iron 3 hydroxide. In every single one of those compounds, oxygen has an oxidation number of -2. Then we have some peroxides. A peroxide is a polyatomic ion, O2 2 minus. So we have it here, bound first with hydrogen for hydrogen peroxide, and next it's sodium peroxide. Each of those has a -1 charge. or oxygen, I should say, has a -1 oxidation number, not a -1 charge. And of course, fluorine is a bigger jerk than oxygen is, so it will take its -1 charge, which will force oxygen, in those rare cases where they interact, to take a positive charge. And that positive charge is based on whatever charge fluorine has. So here, FO2, fluorine dioxide, oxygen has a oxidation number of +1/2. And in our final rule, we have the halogens. The halogens are a little simpler. They are always going to be -1 unless they're bound with oxygen or fluorine. And here we have some examples. Okay, so chlorine, bromine, and iodine are the 3 halogens we need to concern ourselves with. Fluorine is also a halogen, but it's, a special case. So they're always -1. So the simple ones, we have sodium chloride, hydrogen bromide, aluminum iodide. The halogens are all -1. Oxygen and fluorine can force them to take other oxidation numbers. So perchlorate, chlorine is +7. Bromite, bromine is +3. Iodate, iodine is +5. Down below we have some fluorine compounds. Chlorine trifluoride, chlorine is +3. Bromine difluoride, bromine is +2. And iodine fluoride, iodine is +1. All right. So now that we've seen the rules, let's go ahead and work our way through a few examples. I recommend for all your oxidation number work that you be careful, write everything down. It's really easy to lose track of things, especially when you've got lots of numbers dancing around. So our first example is carbonate here. The individual oxidation numbers have to add up to the charge on the compound. So 1 carbon plus 3 oxygens gets us a total of -2. Now, oxygen is not a peroxide, and it's not bound to fluorine, so its oxidation number is -2. So let's go through the algebra. 1 carbon plus 3 oxygens, or 3 times -2, is -2. 1 carbon plus -6 is equal to -2. You add 6 to both sides. That gets you 1 carbon is equal to +4. And that is the oxidation number for carbon. Okay, 4+. So now we have the oxidation numbers for both of the elements in this compound. Let's go ahead and move on to our next example, thiosulfate. Now, thiosulfate is S2O3 2-. The individual oxidation numbers need to add up to the total charge of the compound still, so it's 2S plus 3O equals -2. Oxygen, still not a peroxide, still not bound to fluorine, it's still -2. So let's run through the algebra. 2S plus 3 times -2 equals -2. 2S minus 6 equals -2. We add 6 to both sides. That gets us 2S equals +4. You divide both sides by 2, and S equals +2. So that is the oxidation number on sulfur in this compound, +2. And the oxidation number on oxygen, -2. We have the oxidation numbers on all the elements in the compound. So still fairly straightforward. It's only slightly more complicated. Let's move on to ammonium chloride. Okay, now ammonium chloride might look a little bit more complicated, NH4Cl. It's got 3 elements in it, but that doesn't really change any of the work. We still have to add up to the total charge on the compound. 1 nitrogen plus 4 hydrogens plus 1 chlorine equals 0. So we just look and see which of these elements we can figure out directly. Chlorine, it's not bound to oxygen or fluorine, so it's just -1. Hydrogen, well, it's not bound to a metal, so it's +1, which means we can figure out nitrogen simply enough. We just do the algebra. 1n plus 4 times +1 plus 1 times -1 equals 0. So 1n plus 4 minus 1 equals 0. 1n plus 3 equals 0. and that means that 1n equals -3, and the oxidation number on nitrogen is -3, or 3 minus. So finding oxidation numbers, you do a little bit of work, but it's not particularly nasty. And with that, we've run up against the 15-minute time limit that I set for our videos. So let's end it here, and when we come back, we'll move on and continue our discussion of redox reactions.